Hello everyone. In this lecture we are going to understand how to graphically solve a linear programming problem. So let's begin. So before I actually tell you the technique of graphically solving a linear programming problem, let me tell you a few remarks about it. This technique only works for those linear programming problems which are having exactly two decision variables. And if the number of variables is more than 2, then we need another technique known as simplex method. So right now in this lecture we are just going to focus on the LPPs having exactly two decision variables. So let me recall you how does a linear programming problem looks like. It is having a sense of optimization, which is maximize or minimize. Objective function z equals to c transpose x subjected to ax equals to b x non-negative, where x is x1, x2. So this capital X is the unknown decision variable vector, c transpose x is the value of the objective function, and ax equals to b is the set of constraints, and capital X greater than equals to 0 is the non-negativity restrictions. So all of these things are always given to us in the question. So we need to find the optimal solution of this linear programming problem. So basically the solution technique is divided in two steps. The first step is determining the feasible region. That means the set of all possible feasible solutions of linear programming problem. So firstly we'll be interested in the solutions of feasible solutions of LPP, and then out of all these feasible solutions we will be choosing the best one, which is called the optimal solution, and that is going to either maximize or minimize the objective function, whatever the kind of problem given to us. So let's look at what will be the possibilities. So basically we'll be having two kind of possibilities in graphical technique. First case is we will have a bounded feasible region, and in second case we will have unbounded feasible region. So whenever the feasible region is bounded, in that case optimal solution always exists, while in unbounded feasible region the optimal solution may or may not exist. That depends upon example to example. So we have various possibilities here. So let's explore all of these possibilities through examples. So the first example I have taken here is a maximization problem in which I am maximizing 5x1 plus 4x2. These are the constraints given to me and the non-negativity restrictions. So the first thing you have to draw is drawing the feasible region, and to draw the feasible region firstly I have to draw the constraints. So these constraints are nothing, if you look at these constraints are nothing but the inequalities. So first thing is you treat these inequalities as equations. So the first line I am going to draw is this, and the second line I am going to draw is this. So to draw the line x1 plus x2 equals to 3, I have already marked the points 3, 0 and 0, 3, and then we just need to join them to get the first line of constraint. And similarly you draw the second line of constraints by marking the points 4, 0 and 0, 8 by 3. So joining them I will be getting my second constraint. So once you have drawn the lines of constraints, then basically you have to look at their sign of inequalities, because actually the constraints are not equations, they are having certain regions. So since this is the line, say you have just drawn x1 plus x2 equals to 3, so x1 plus x2 less than equals to 3 will be a region. Either it will be this side or it will be this side to this line. So to actually decide which side is the region marked by x1 plus x2 less than equals to 3, you take any reference point. Usually we take origin. So you put 0, 0 in this. So I am getting 0 plus 0 is less than equals to 3, which is actually true because I know 0 is less than equals to 3. So that means we have to mark the region of that side which contains the point 0, 0 because 0, 0 is satisfying the inequality. Similarly, you decide the regions of all the other respective constraints by choosing the reference point like that. So doing this, what I have done, I have marked the feasible region like that, and keeping in mind I have to draw my feasible region in the first quadrant only because the non-negativity restrictions are also given to me. So this is how I'm getting this A, B, C, D as my feasible region, where C is 1, 2. The coordinates of A, B, D had already been written because we were drawing the lines, but C is the intersection of these two lines which I have drawn. So you need to find the coordinates of C. They are turning out to be 1, 2. So this is an example where we are getting a bounded feasible region. Remember, I just told you there will be two possibilities. So this is the first possibility. We are getting a bounded feasible region A, B, C, D. And these A, B, C, D are called corner points or extreme points of the feasible region. Now, as per the fundamental theorem of LPP, the optimal solution exists at one of the corner points. Okay, so let me tell you, we are done with the first step. I told you the solution technique is divided in two steps. The first step involves finding the feasible region. So we have already found the feasible region. Now we are looking for the best solution. And the best solution is existing at one of the corner points out of A, B, C and D. So what we'll do, we'll make a list here. On one side, we'll be writing the corner points. On another side, we'll be writing the value of Z. So A, B with the respective coordinates on one side, and on other side, I'll be computing the value of Z by substituting these points into the objective function, which is 5x1 plus 4x2. So you substitute them and get the respective values of objective functions. So the A is giving me 0, B is giving me 15, C is giving me 13, D is giving me 32 by 3, and out of all of these, 15 is the maximum. And why I have marked the maximum? Because you look at the sense of optimization of your given question is maximize. So I have selected my optimal solution. So clearly this B 3, 0 is the optimal solution. So that's how easy it is to graphically solve a linear programming problem and concluding the optimal solution. So remember, in this example, because of the bounded feasible region, it was guaranteed that optimal will exist, and by fundamental theorem of LPP, we know that optimal is going to exist at one of the corner points. So it was sufficient to look at the corner points and compute the value of Z. So this is our final optimal solution which we are getting. So that's about example 1. So let's look at example 2, in which I have given a different LPP. It's maximize Z equals to 4x1 plus 6x2. However, I have kept the set of constraints exactly same as example 1. So there will be no change in the feasible region. The only change is going to be in the objective function. That's why the only change is going to be in the optimal solution. So exactly on the similar lines, I have drawn the feasible region very quickly, and it's actually turning out to be exactly same. Even the corner points are same. So at each corner point, I need to now just evaluate the value of Z. So Z is different than the example 1. So different values of Z I'm getting here, 0, 12, 16 and 16. And as you can see, at 2 of the points I'm getting Z same. So these both C and D are nothing but my optimal solution. So that's the contrasting difference between this example and the previous example, that although the feasible region is same, but in that example we were getting exactly a unique optimal solution, because the maximum values was occurring at exactly 1 point. But here the maximum value is occurring at more than 1 point, and these 2 points are C and D. So both of these are optimal solutions. So in fact, the number of optimal solutions is infinite, because if you will be finding any point on the line joining C and D, so at C also your Z is 16, at D also your Z is 16. So at both the points Z is same, and in fact at all the points lying on the line segment CD, Z is turning out to be 16. So that means all of these are the optimal solutions. So CD is the optimal edge in this case. So we have infinitely many optimal solutions. So the conclusion from these two examples which we can draw is the number of optimal solutions of a linear programming problem is either 1 or infinite, because in this example we felt that the number of optimal solution is 2, but actually whenever two optimal solutions are there, they're all convex linear combinations. That means the line segment joining those two optimal solutions is also the optimal solution. So actually the number becomes infinite. So it's either 1 or infinite. And keep in mind this word which I've just written, if exist. What is the meaning of if exist? So just recall, I told you in the beginning that in bounded feasible region there is guarantee that the optimal solution is definitely going to exist, but in unbounded feasible region it may or may not exist. That's why the word if exist is coming here. So before moving to example 3, let's try to understand why this happened in this particular example, that instead of getting one solution I was getting infinitely many optimal solutions. This is happening because the slope of the line of objective function is matching with the slope of one of the constraints. So if you write this like 2 times 2x1 plus 3x2, so that means the objective function slope is nothing but this. So this is a scalar multiple of this. So the negative slope of that is same as one of the constraints. So if you will be drawing the line of objective function, it will be parallel to this constraint. So in these cases always you are going to get, if that is optimal edge, you are always going to get most likely infinitely many optimal solutions instead of unique. So you keep track on the slope of the line of objective function, that if that matches with one of the constraints, then possibility is you might get infinitely many optimal solutions. So now let's move to next example, example 3. Here I've done a little change. This is still maximize z equals to, I have changed the objective function x1 plus 3x2. I have kept the constraints similar, except that I have changed their sign. If you look here, the sign are now greater than equals to, while in the previous two examples both of these were less than equal to. So because of change in the sign of inequalities, what is going to happen? The feasible region is going to change, because see, this is the line, say x1 plus x2 equals to 3. So this time x1 plus x2 greater than equals to 3 will be this side, because 0 plus 0 greater than equal to 3 is not true. So that means the opposite side region will be marked, which does not contain 0 comma 0. Similarly for the other line also the region will be this. So if you do that, you will see that the feasible region which you are going to get is lying on the outer side, and this is nothing but unbounded feasible region, because both of the constraints had a greater than equal to sign. So whenever you put the reference point in between, both of them are giving you region away from 0 comma 0, which is extended outwards, and this is an example of unbounded feasible region. So you remember we talked about the second possibility. So what to do when you get unbounded feasible region? So the technique which we used for bounded feasible region will not work here, because for bounded feasible region it was guaranteed that optimal solution will exist at one of the corner points, but for unbounded feasible region we do not know whether the optimal solution is going to exist or not. So we really cannot do it exactly in a similar way as we did for bounded. So here we have to altogether apply a new technique, and that involves to draw the line of objective function. This technique also you can use for bounded, but unbounded feasible region questions have to be done by this technique. So you draw the line of objective function. What do you mean by line of objective function? You give an arbitrary value to z. Here I have given it z equals to 6. See, this is your z which is given to you. You give it any arbitrary value. I have given it z equals to 6, and then you draw the line x1 plus 3x2 equals to 6. So when you will be drawing this, you will be getting this as a line in your feasible region. I have shown it with a different color and dotted because I have to distinguish it from the lines of constraints. So the line of objective function should be distinguishable from the line of constraints. So this is z equals to 6. After drawing this line, I have to figure out that which is the direction of z increasing, because now I either have to maximize or minimize. So you choose an arbitrary point on any side of the line. Say here I have chosen 4,3 on this side, and in this z is turning out to be 13 on 4,3, which is greater than 6. So that means this side direction in which z is increasing. So whenever you draw the line of objective function, after that on either side of the line you choose an arbitrary point and look that the value of z is higher or lower. If the value of z is higher as compared to what the value is on the line, so that means that is the direction in which z is increasing. Therefore, to maximize z, I have to move in this direction. So this step is called identifying the direction of z increases or decreases. Here we are maximizing, so I have identified the direction in which z increases. So after identifying this direction, you virtually move this line parallel to itself in that direction in which z increases and try to find a stopping point. Since here I can see this line can be moved indefinitely parallel to itself because there is no stopping in that direction because the feasible region is unbounded. So the conclusion is that this LPP is not having any optimal solution, or in other words we say LPP is unbounded. So that's the meaning of unbounded LPP. LPP is said to be unbounded if optimal solution does not exist. So here we got the first possibility that in an unbounded feasible region, the optimal may or may not exist. So in this example, it is not existing. So let's have another example. So here I have kept the constraints similar. So that's why the same feasible region you are getting, while I have changed the objective function to minimize this time x1 plus 3x2. So even the objective function I have kept similar. If you compare with example 3, I have just changed the sense of optimization of the question from maximize to minimize. So this time we'll be interested in moving the line of objective function in the direction in which z decreases. See, we just figured out that this is the direction of z increases. So obviously this is going to be the direction of z decreases. So I have to move that line parallel to itself in which z is going to decrease because I have to minimize. So moving this line here, I have to stop at the last point of the feasible region because after that I don't want to go out of the feasible region. So moving in that direction, you figure out what is the last point which you encounter while moving in that direction. So 4,0 is the last point which I'll encounter, so that I'll be declaring as my optimal solution. So z minimum is turning out to be 4 at the point 4,0. So x1 is 4, x2 is 0 is the optimal solution. So this is another example of its kind, that although the feasible region is unbounded, but my LPP is having existing optimal solution. In other words, this is called feasible region is unbounded, but LPP is bounded. So there should be a clear-cut distinction between these two. That is, optimal solution exists. So I've given you both examples that in an unbounded feasible region optimal may or may not exist. Let's look at one more example. In this also I have kept the feasible region same, which is unbounded. So that means the set of constraints is same, but I have changed the objective function this time again. It's still minimized, but I have changed z is equal to say 2x1 plus 2x2 subjected to same set of constraints which were giving me the unbounded feasible region. So here you follow the same procedure. You draw the line of objective function by giving it any arbitrary value. I have given it z equals to 8. So you need to draw 2x1 plus 2x2 equals to 8. So this is the line of objective function. So you mark 4, 0 and 0, 4 and join these 2 points to draw the line of objective function on which z equals to 8, and then on either side you calculate z at any random point. So I have computed at 4, 4 turning out to be 16, which is higher than 8. So this is the direction of increment, other side is the direction of z decreases. And now you look at your question is minimize, so you will be moving in the direction of z decreasing, and in this direction I have to figure out the last point of the feasible region. So here it's not one point, but it's actually a combination. It's the edge joining 2 points 0, 3 and 1, 2. So in this case also I am getting more than one optimal solution. 0, 3 is also giving me z6 and 1, 2 also giving me z6. So instead of writing 2 optimal solution, I know the conclusion is infinitely many optimal solutions. So this is the last example of its kind. So this is reminding you of example 2, in which because the line of objective function was parallel to one of the constraints, we were getting infinitely many optimal solution. So exactly same thing is happening here. You look at the slope of this. So this is 2 times x1 plus x2. So this is obviously parallel to this constraint, x1 plus x2 greater than equals to 3. So when you will be moving this in this direction, instead of getting one point unique as the last point of the feasible region, you will be getting complete edge adjoining the line of objective function, because it matches with the line of constraint because their slopes are same. So that's why you are getting here infinitely many optimal solutions. So here we are to draw the conclusion about graphical solution. In LPP with bounded feasible region, so I'm just concluding what we have just seen in these 5 examples. In LPP with bounded feasible region, optimal solution always exists, and in LPP with unbounded feasible region, this is something which I told you in the beginning, I'm just concluding that optimal solution may or may not exist. We have seen examples of both the kinds, one existing and one not existing. And then what else we saw? That whenever the optimal solution exists, so you can comment on how many optimal solution exist. So it is either a unique one or the number of optimal solution is infinite. There is nothing in between. You cannot say give me a LPP with having exactly 2 optimal solution or exactly 3. Whenever it is 2 or 3, that means it is infinite, or it is just the unique. So that's all about graphical solution of LPP. Thank you.